And thanks very much to Nathan and David and Adrian, who's not here, I think, for the organisation of such a great conference. And I've enjoyed every talk so far, so that's great. You'll have enjoyed every talk up until now, but anyway. Okay, so... so the talk, it's what's about dipolar geophysical vortices. It's joint work with Matthew Crowe, who's also currently at UCL. Unfortunately, we're losing him. He's going up to Newcastle this summer, unfortunately. So, okay, what's it about? One of these. Ah, yes, that's true. Gee, this modern technology, yeah. So I'll talk about two things if I don't run out of time. The first is a model that was prompted by some observational work by these people, Ni, Zai, Wang, and Chris Hughes. They argued that dipoles are widespread in the global ocean, and in particular, he made these comments: the mesoscale dipoles are widespread features of the global ocean, having a relative uniform 3D structure that can lead to strong vertical exchanges. So I'll try and present a trivial model, actually, that has some of those properties, and then move on to the decay of dipolar vortices in general, in particular deriving it for the stratified vertical slice model, but it applies to the beta plane exactly the same. In fact, Vladimir's already made a comment about this, that this is the case where the dipole propagates in the same direction as the Rossby waves, coincides with the phase speed of the Rossby waves, and they carry away the energy from the dipole. So I hope I escaped from this slide here, because this would be like, if you've ever been in a seminar where Michael McIntyre is in it, the speaker quite often gets to his first slide and he never gets off it. So, so these are the observations by Ni et al. What they did was they took, I assume, sea surface elevation over the global ocean, observed sea surface elevation, of course, from satellites. They then had an algorithm which searched for dipoles. They defined a dipole as two regions of vorticity that were close together in some sense. They then chose the ones that had pairs, and they then normalized the distance between the maxima of the negative vortex and the maximum of the positive vortex. They normalized that to 1, and then they averaged everything using that. And this is what they got. This is their composite dipole, as they call it. So a large dipole here with very small outriders. This is the 2D pressure distribution, surface pressure. This is a cross-section, I guess, along this line, just to show you what the pressure looks like. So they are the observed values normalized so that the distance between here is 1. No. This has been, no, these are all, then they've just been rotated so that this point here is 1, 0, and this point here is -1, 0. Yep. And then they obtained what they hoped would be simultaneous subsurface pressure from Argos floats. So they had all the data from Argos floats, and this is the subsurface pressures using the same normalizations as this, and they run down to about 1,500 meters. And this is the subsurface profile that they get, the average subsurface profile. So that's what we'd like to reproduce. Can we reproduce this? So what shall we use? Well, we do use the usual thing: geostrophy, hydrostatic, nonlinear, of course, conservation of density, and then you get what's come to be called the surface geostrophic equations, an interior PV that's advected around, and the surface PV that's advected around on the surface. Okay. So what do we look for? And of course, I should be nervous there because I've heard at least two people run down the surface geostrophic equations this morning. Bill saying that he doesn't believe them, and then Joe over lunch saying that he didn't like them. Well, okay, so here we are. We'll assume that the interior PV is 0, so we don't have to do that, but let's take the interior PV to be 0. Well, that's nice. That satisfies the nonlinear equation, and of course, any flow started from rest will look like that. Then are we looking for a steady flow here? It's a steady flow. We're looking for something that's advancing in the positive x direction. In this case, because we're on the F plane, that means that's irrelevant, the direction, it's just a direction. And so this is the lower boundary condition. It's just the uniform velocity plus the stream function, the pressure advecting around the density. And then if we go far enough down, the density perturbation disappears. So there's a governing equation. It's, of course, nonlinear. We want solutions for this. And the classic way to find a solution, really first used by Chaplegan and Lamb for barotropic vortices, is we just assume that it's a linear function. And that's, of course, going to satisfy this equation. PZ is a linear function. And, of course, it gives us a linear equation, so we can solve it. K, we have to find. It's some constant wave number. And the only other thing we have is that for a steady solution, of course, in the frame, co-moving frame, the boundary of the surface PV must be a streamline to satisfy this equation. Interestingly enough, the boundary of the vortex, in a sense, where the non is, doesn't have to be we don't have to have closed streamlines below the surface because the PV is conserved irrespectively. And so that's it. There's our final. So that's a problem we want to solve. We realized we weren't the first people who'd looked at this. Buraki and Snyder had looked at exactly that problem. And the idea is now you just pose a solution, which is sine theta, that's the y dependence, times some arbitrary function of r and z. If you pose it this way, this will automatically satisfy the Bessel's equation in the horizontal with an exponential decay. So this automatically satisfies the zero interior PV equation, and you end up with two integral equations now. This is the equation for, if you like, the density. The density outside the eddy has to vanish, and then we've got that linear relation inside the eddy. So they got two equations of this form. They then parameterized A. We'll see later we'll see very quickly that A is a very slowly varying decaying function. So they parameterized A with 512 points. They then had a 512 by 512 system that they chose a value of K. They inverted their 512 by 512 system. That did not satisfy K equals R, so then they nonlinearly iterated on K, and eventually they got a solution. Well, in fact, it turns out there's a technique that was designed for these forms of integral equations by Tranter. It's a very beautiful piece of work in a monograph by Tranter. And in fact, what we do instead is we hypothesize that A can be expressed as a sum of these Bessel functions. And that immediately shows you that at large xi, this only decays like xi to the minus a half. It's a Bessel function. So that's why they needed so many points to approximate this. Okay, so here's A. We stick A into here, and Tranter's method works, because when we integrate A against the Bessel function for r greater than 1, it's called the Weber something or other, Weber somebody or other integral, discontinuous integrals, it's 0 for r greater than 1. So it automatically satisfies this condition. In fact, we don't need it, but it also happens just to be a simple polynomial. It's a polynomial of degree 2n plus 1. So one of these is just a polynomial. This one, I guess, is just a polynomial of degree 2n plus 1 in R. So what have we got? Here we are. We just substitute it in. This is the only thing now we've got to satisfy. And again, it was a cute observation by Tranter. This, of course, if we take the inverse Hankel transform, because this is just a Hankel transform, multiplied by J1 of xi r divided by xi, then we get exactly this. We find out that that visualization is telling us is that this function here is the Hankel transform of our polynomials. So in fact, we can replace the J2n plus 1 over xi's here by this function. Okay. Moreover, these are sorry? Yeah, we've got to stick another xi up, as you see, another xi pops in. Yeah, yeah. So where were we? Oh, yeah. This is, these functions are orthogonal over 0, 1 with weight function r. So we multiply by r times those. We multiply this equation through by r times that. One of them's obvious. This one will only give one term. You get an r squared rm, and that's this term. So the right-hand side just becomes this Kronecker delta. So it's just 0. It's only non-zero for the first line, and it's 0 below the first line. There, are there some C's? I've lost. I can see this C. Oh, this C. No, this C is different. Capital C is a matrix, and this is a vector. Yep. Yep. So what happens? This one gives us B. There it is. We've just replaced this Jn plus 2 over xi comes in here when the Jm, this J1m, sorry, J1 of xi combines with Rm to give us J2m plus 2, and here's the J2n plus 2 over xi. That's this term, and this term here gives us these integrals. So we've transformed this equation using Tranter's method into a simple matrix equation. And moreover, because of these orthogonality properties, B is in fact the identity matrix. So B is the identity matrix, and C, remarkably, has an analytic evaluation as just a rational function. So it's just a rational function of the m's and n's. So we know it explicitly to arbitrary precision. So in fact, this is just a standard eigenvalue problem. Well, yeah, algebraic eigenvalue problem, yep. There's only one trick. I left out the word inhomogeneous. It's an inhomogeneous eigenvalue problem because C is not 0. The first element of C is 0, is non-zero. Just like any eigenvalue problem anyway, it's non-unique, but it's made unique by that other condition that the boundary of the street, that the density distribution has to be continuous across the boundary of the vortex. So we have this final condition. But this is good. It absolutely is. I mean, you could build one that wasn't, but it wouldn't agree with the data. You could, of course, just like who's the people who Sadowski did this many years ago for the Euler vortices. Yeah, you can put a jump in. It's a jump in the pressure there, Be interesting if you put a jump in the density. In fact, in the SQG, a jump in the density means an infinite tangential velocity. So if you want to keep our tangential velocities fine, sorry? Absolutely. We can talk about it later, but it's absolutely true that a jump in PZ on the surface of a 2D SQG gives you an infinite tangential velocity. And I think people who do quantum dynamics with it, what they do is that they factor that infinite velocity out because they just use the normal velocity. Would that be a true statement? Yeah.
It's a logarithmic singularity.
Yeah, absolutely. In fact, there's a very nice talk by Hunter last week on that. Okay, but this is good because these problems, there's actually almost no theory. If you look up the theory of inhomogeneous eigenvalue problems, there's almost no theory on them. So that's not...
Can I teach that?
Yes, you have to not only you have to derive it, but the good thing about this is that this inhomogeneity is only in one line. So all we do is we use this to eliminate A0 from all the lines below the top one, and we just deal with that. And then, so there it is, we just eliminate A0. Now we've got a standard eigenvalue problem. And in fact, if we just solve on a 12 by 12 matrix, we get 4 decimal places that agrees with Miyake and Snyder. So we can do it on a 12 by 12. And then we haven't determined A just like it's in a standard eigenvalue problem, it's non-determined, but we haven't used the first condition. So now we use the first row that we've been neglecting, and that gives us the normalization. And now we've finished, we've got the final solution. This is the surface buoyancy, 0 outside, and a sum of these polynomials inside. So that was the solution. What's it look like? Here it is. This is the first mode. This is our first mode number. This is the pressure in red, which decays slowly to infinity. This is PZ is the green, and the blue is what should be equal to it. Inside is K into P plus R, and so that's the blue dashed line, which coincides inside, but of course outside it doesn't have to, and it doesn't. And this is a picture of that eddy. One thing that this method gives you, of course, is it gives you all the eigenvalues. So we can get the second mode as well. Here's the second mode, pressure and surface buoyancy. And this is a picture of the second mode. Sorry, this is this the buoyancy? No, this is the pressure. This is a cross section of the buoyancy. If you want to look at the green, that would be a cross section along here of the buoyancy. So it would be negative and then positive and then 0. This,
if you go from top to bottom,
oh, okay. So this is just from the origin. So it goes origin, negative, yeah, just half, yeah. And as you might expect, the mode 1 is stable, insofar stable under the numeric norm, in that you can run it for a long, long time and it doesn't change. Mode 2 is not stable under the numeric norm, that if you run it, it looks like this is t equals 2, looks okay, but by about 3 eddy turnover times, it's starting to look problematic, and by 3.5 eddy turnover times, it's broken down. So this is not a long-lived solution of the equations. It lives for a little while, but it doesn't live for a long while. Yes, yep. Yeah. And So now let's make a dipole. They made a dipole by averaging all their observations. We'll do the same, and we'll include mode 2. We can include it. We're not claiming that this dipole that we're making, our composite dipole, is a permanent structure of the equations. It consists of something that could almost be a permanent structure by something that lives for a little while. And so we've got 80% of mode 1, and we're saying we've got about 20% of mode 2. Because, of course, that's what they could have. They're just looking at instantaneous snapshots. So they can have long-lived structures in there, but they can have also instantaneous structures. So we'd argue this is the same. It doesn't make a big difference, really, but as you'd imagine, it just lets us get a closer fit. Well, with time, it'll break apart. If you ran this as an initial condition.
Only mode 2, mode 1.
Yeah. So if you add the two together, stuck them into a nonlinear numerical model, then mode 1 would propagate faster, and mode 2 would get left behind. I think it'd collapse. Yeah. Yeah, because it. But if they're circular, then we've sort of found all the circular solutions. Yeah, it could survive. We'd never tried that. Yeah, but yeah, yes, it's true, absolutely. But that's irrelevant because remember, their structures don't live. They're just taking a picture, so it can. So we're just constructing a picture. All it has to do is be a picture. No, but you do see the point. And so I wouldn't put it forward. If you asked me to initialize a model, I would initialize it with mode 1. And I would never throw in E mode 2. I'm just trying to explain their observations. Yeah, I would never stick this into a model because I would think it was interesting, but sticking to mode 1, that's more interesting. Yeah, because that's a long-lived structure. Yeah. And I wouldn't expect this ever to emerge in a model. But we're just trying to model their observations, if that seems reasonable. Yeah. So here it is. The solid line is the composite model dipole. The dashed line is the composite observed dipole. This is the decay scale of the various modes. So that red is mode 1, blue is mode 2, which has a slower decay scale. The dashed black line is the observations, and there's a solid black line there, which is the theory. Really, you can see the decay, it's an exponential decay in a uniform stratification. So that's it, I think. That's probably all we did on that problem. Do we? I know, here's some comparison. Yeah, please. Okay, no, we didn't have to assume it was weak, but right back at the start, we assumed it was uniform F, N. Now, you could solve it for a different N, you'd get a slightly different decay scale. And
Just use that as
here, yes, yeah, absolutely. So this has got an adjustable parameter, which makes life easier. Here's a comparison. What is going on here? Oh, this is their surface pressure distribution, and this is the one that the model gives. This is their subsurface pressure distribution, and this is the one that the model gives. As you say, there's adjustable parameters. Both of us have normalized the surface to a particular value, same value, because it's a linear problem, and we've normalized the decay scale.
right. Not different from that.
They're pretty similar. I would like to think they were similar, yeah. Thank you. Yeah. They're on different scale. That's right, because if they squash, their scale is not, whatever you call it, isotropic, is it? Yeah, let's hope so.
It's also a function
That's true.
Could look better
Uh,
than you can't do level.
uh,
It's better than it looks. Just
oh,
scan it on.
thank you. Good. And then they were very interested in the vertical velocity fields because they were pointing out that these eddies, these dipoles, could be important for, well, they're talking about frontogenesis and vertical velocities. So this is the vertical velocities from the model. They come from the nonlinear, the only really nonlinear part of the problem is, this is the density equation, non-dimensionalized, and that's where we get the vertical velocities from. There was some discussion in their paper, they thought it might come from Ekman pumping or something else. You don't really need Ekman pumping, you just get it from the density distribution. And what you're saying, of course, is that the velocity, the perturbation velocity advection of the background vorticity is balanced by the leading order advection of the perturbation vorticity. And these are the observations, but of course they have calculated this using a model, and these are what you get from that model. So I think that was that topic finished. How are we doing for time? Okay, hold on. Okay, so let's go here then. Whoops. So the other topic then is, well, that's all right. We found this vortex, and if they're small enough on the beta plane, they're not going to be affected by Rossby waves. But maybe if they're too big, they'll be affected, and so if they lie in the Rossby wave range, they will radiate and die. So let's just look in general at dipolar vortices when they're in a dispersive media. And let's look at, it gives you, it's a bit actually a more general problem, is we'll look at a stratified vertical slice model. So this is a vertically stratified flow, uniform, and we're going to have a vortex propagating to the right at constant speed u, n squared is a constant, and so it's going to generate internal waves, and therefore it'll die eventually. So that's our model, constant n, no diffusion, 2D vertical slice. The axes are fixed in the fluid so that we can use linearized equations eventually. So we're going to keep, all axes will always be fixed in the fluid, even though some of the quantities won't be. Okay, so it's disturbed by a circular Lamb-Chaplygin vortex, classical Lamb-Chaplygin vortex, a dipole of radius a, propagating at speed u. And so we could do something, we assume that the inverse Froude number is small. And that, of course, is just saying that the vortex is tiny and the waves are large. So it's just a little point moving along that's going to excite waves. So on the scale of the waves, then the vortex appears just as a small region of order area epsilon squared. The pressure, and so therefore the wave field will be governed by linear dynamics. The vortex is nonlinear, but the wave is linear. And then it's only the length of the boundary of the vortex is only of order epsilon, so it's going to exert a drag of, the waves are going to exert a drag of order epsilon cubed on the vortex. And so the vortex is going to be modified over timescale. It's advection time, A over U, over epsilon cubed, which is very long. So it can take a long time for this vortex to die in this limit. Okay, so therefore we're going to make this hypothesis that the response of the vortex to the drag is to evolve so as to remain a Lamb-Chaplygin dipole, but with the radius and speed varying slowly with time. So it'll keep the Lamb-Chaplygin form, but it'll just change radius and speed. So like an adiabatic variation. Oops, where are we? Okay, it'll pop back up the actual vortex, but it is the Lamb-Chaplegan vortex.
So it's not the one you...
No, we've jumped away. Well, it'd be nice to do that, and we're looking at that at the moment, but this one is not that one. No, this is just, when we put this on a beta plane, it'll just become a barotropic problem. So there's an ignorable coordinate. In this case, this one's a vertical slice model, so the ignorable coordinate is the coordinate into the page. This is a cylindrical vortex, an infinite cylinder. Or on the beta plane, it's an infinite vertical cylinder, which is the Resnick and Lavachov did it for the case when it's going in the other direction, so it doesn't generate waves. If it goes faster than all the waves, that's right, or if it goes in the other direction. That's it. Absolutely. Yeah. The one on the beta plane, this one does, of course. On the beta plane, it's the Rossby waves. Yeah. Okay, so where are we? Sorry. The internal wave field is set up over, we'll see this in the integrations, but it's obviously it's set up as the vortex moves along, it just leaves the internal wave field behind it. So it's set up over a timescale of order, the advection time, so it could be taken as quasi-steady over this time. And secondly, so finally, what do we need then to stitch this together? We need to know the vortex energy. We need to know the wave drag, because that'll give us the rate of change. And it turns out, because we've got two unknowns, we need another equation. And it'll turn out the best one to use is to use the vortex center. So what are our equations? Here they are. This is just the non-rotating Booz-and-Esch equations in 2D for a vertical slice. The horizontal momentum, vertical momentum, density, and incompressibility. We then look for steady solutions. We look for steady solutions where this allows us to introduce a stream function, and we're pretty much back in the old position. Here is the total velocity times the advection of the horizontal vorticity. This is horizontal vorticity is generated by a horizontal gradient in the buoyancy, and then the buoyancy. This is the advection of the total buoyancy consisting of the background buoyancy and the perturbation buoyancy. And we want steady solutions to that. And so, of course, we now know what to do. We just assume that everything's linear. So now that's the full problem. If we look just on small scales, is that the full problem? It is. If we look on a small scale, we can neglect the buoyancy equation and we can drop the buoyancy out here, and we just want that the vorticity is advected by the background flow, and that's Lamb-Chaplegan. And so this is the Lamb-Chaplegan solution. It's just a uniform flow. It's a Bessel function. You can just solve it directly. A Bessel function with some constant times a Bessel function. And outside, it's just a dipole, Z over R squared. So it's a dipole outside, and inside it's this form. This K plays the same role as the K did in the SQG model. It's just an eigenvalue, but here it's easy to find. It's equal to, or its product with A is equal to the first zero of the Bessel function, so we know what it is. So that means A is determined when K is known, because the product has to equal this. And then we demand continuity of the tangential velocity. We insist that there's no vortex sheet at the edge of the Lamb-Chaplegan vortex, and that forces C to be this value. And importantly, we can just compute the energy of the vortex. It's just vorticity against the stream function, and this is the energy of the vortex. So that's the energy of just of the Lambda-Plegan vortex. How about the wake? Well, here's the wake. We said we're a long way away, so the vortex is just a point, and here it is. It's a dipole sitting on the z-axis. So this is it, d by dx of sig and x, a dipole. And so we just solve it. We just solve it by Fourier transforms. And this is the Fourier transform solution. The interesting thing about it is, of course, that you've got to make sure you get the radiation condition right. When it's decaying, you're fine. So if the waves are short enough, I guess it is, k is large enough, it's just an exponential decay. If the waves are too long, then you've got to be careful and make sure you've got outgoing waves. And you get that from the group velocity. And then you can work out the pressure. It's very nice. You just write down the pressure. It's the vertical energy flux is actually given by the pressure integrated against the vertical velocity. We substitute that in, and you now use Parsifal's theorem, and you can just write it down from here. And so this is the work done by the drag force, and that must balance the loss of energy. Energy equals work, or negative work. So we've got one equation now, d by dt of E equals that. We need another equation, and Glenn Flill with Haynes had worked this out. They've done this problem for the dipole on a beta plane, and they tried a number of things, but eventually made this argument, which is a very nice argument, that they took the total streamline sufficiently close to the vortex center so that it was closed. They integrated over that closed region. This is what you get, integrating the equations. These terms drop out because we've got bounded by a streamline, so u dot n is 0, and we've just got d eta by dt or dB by dt, if you like, is 0, and we get d eta by dt is actually 0 as well. The total density perturbation vanishes. And so we've got this quantity, the integral over this area is 0, but we now let that area vanish. We go closer and closer to the maximum of the vorticity, and then we just get approximately the value at the center times the area. And so therefore we find that eta t and bt should vanish at the vortex center. And so that's our final equation. We get that the vorticity at the center of the vortex, not necessarily the maximum vorticity, it generally is, but the center of the vortex is, and the buoyancy at the center of the vortex should be constants of the motion. Now we've got what we need. We've got two equations and two unknowns. We can just put them together. So this is energy work equation. This is we're going to take the center vorticity to be a constant. The center vorticity, because it's Lambda-Plegan, is just going to scale as u over a, just the scale for vorticity. And so we're saying that u over a should be a constant. And therefore we just substitute this in here and integrate. And there's our prediction for the decrease in radius of the vortex. And as expected, it's proportional to epsilon cubed. Here are some examples. On the left-hand side is hidden by the figures of psi, and on the right-hand side is buoyancy. So let's see. Work. So the dipole is where the green is. This frame is moving at constant speed to the right. The initial position is black, and so that's the initial position being left behind, and the vortex is moving slightly because it doesn't move at uniform speed because it changes. We're going again. So you could see in the neighborhood of the vortex, the flow is becoming steady. So that's the wave field that's impacting on the vortex. And in a sense, it doesn't matter what's happening way farther away, because as long as that's all we needed was it's steady in the neighborhood of the vortex. So there's the vortex moving. The vortex, this has actually got the vortex in it. It's just that's the sort of scale we're looking at. I don't know what value of beta this, or value of epsilon this is. Probably about epsilon equals a tenth, I think. Okay. Let's check a few things. First of all, there's center vorticity. This is the center vorticity. This is after 50 eddy turnovers. It's dropped from 1. Well, for the biggest value, remember our parameter epsilon should be small, but this is epsilon equals a half. So even for, but maybe that's not a nice one, but it's dropped to say for 0.4, but this is 0.95. So it's dropped down about 2 or 3%. Yeah. We argued that the center buoyancy should be constant. The center buoyancy is more erratic. It actually increases for the smallest value, and it's quite erratic. And the reason for that seems to be that we get waves generated, internal waves generated inside, gravity waves inside the vortex core. They don't affect the vorticity. Oh, with those original equations, the full equations. Where are they? These equations. So the solution of those full nonlinear equations. Yep. Oops. Where are we? Whoops. Here we go. This is a comparison between the prediction from the model, which is solid, and the, is that right? Solid? I better be. Solid lines give the numerical integrations, and the dotted lines are the predictions from the model for these values of epsilon, so epsilon 0.1 to 0.5. That's for the maximum, the value of the stream function at the vortex center, which decays, and this is the value of the energy of the vortex, which also, as you expect, decays. And this is the impulse of the vortex, which is actually another conserved quantity. You could use that instead of the energy, but in fact, it makes almost no difference. Well, why is the center vorticity such a useful quantity? Well, here is actually a blow up around the vortex. This is the number of points we were using for those other integrations. And in fact, I think it was 4,000 by 4,000. And this means we get about, I think, 50 points across the vortex. So it's pretty well resolved. And what you're seeing is, this is at time t equals 15. For a big value, epsilon equals a half, you're getting vorticity left behind. But the reason the center vorticity seems to be good is because the center seems to be unaffected by this. So the center vorticity does seem to be conserved and unaffected by the fact that we're losing fluid at the back. Okay, we can add in viscous dissipation. For this limit, provided the Prandtl number is bigger than 1 and the Schmidt number is bigger than 1, then the leading order effect is just the dissipation in the dipole. The Navier-Stokes equations tell us that the dissipation rate is proportional to the entropy. So we could just add in actually the Navier-Stokes dissipation, because these are two small quantities. We could then get an extra term in the decay of the energy of the vortex, and R is the Reynolds number here. So the ratio of these two terms is proportional to epsilon cubed R. So it says that D is what determines the type of dissipation. If D is very large, then it's dominated by wave drag. If D actually is order 1, then it's dominated by viscous flows, because they're of the same order when D is 3 gamma squared. Gamma was our Bessel function root, so about 44. And so as the vortex evolves, the value of D changes. So here are two examples. In this case, the vortex gets fatter due to viscous dissipation before it starts to die. This is the value of D normalized by its maximum value. So we've got to know what its maximum value is. It starts off, in this case, at about 8 and gets bigger. So when it's 8, that means that it's in the limit where where viscous stuff dominates until it passes 44, and then wave drag dominates. So this is starting off down here, actually. This line comes down to here. So it starts off here, and eventually this grows enough so that wave drag dominates. And you can see that it's viscously getting fatter, and then it shrinks. And this one starts off in the wave drag case. D is large initially and stays in the wave drag case, so it just decays. There are a whole stack, of course, of 2D dipoles, so this stuff applies to that. We could have, this is the cylindrical vortex in a slice model. This is Fleal and Haynes vortex on the beta plane. This is a cylindrical vortex going up the axis of a rotating tank, because that's exactly, as Bretherton pointed out, they're the same equations. And of course, we need something to be 2D, so we can actually do it with a spherical vortex in the vertical slice model. Problems that are related but not the same is you can do it for a Hills vortex. This is the Hills vortex moving up the axis of a rotating fluid. So this is the Hills vortex here. This is the wake behind the Hills vortex. And a problem that introduces some other complexities, we can do it for a coastal eddy. So this is an eddy moving along the coast, and there's a topographic shelf here, which ends here. And of course, now it's not an infinite medium to support the waves, so the waves are quantized. And so instead of getting integrals, we get sums, in fact, finite sums of the shelf wave modes. As this thing slows down, it generates more and more modes. And that's it, I think. It is against a wall, that's right. So it's a vortex against a wall. Yeah. And that's it. And here are some references. Okay, thanks very much. Yeah.